So I sent the links to I guess, the three-part Substack series that I'm writing on Mina. For context, I am currently part of their ZK App Builders program. So it's like a grant program, like variable amount of commitment required. It's not like full-time or anything like that. And it's for 11 weeks. So right now it's like week, I think 7-ish or something. And I have a set of posts on like what Mina is and interesting things about MEV on Mina, which is like a culmination of some of the learnings that I've gotten through the first half of the Builders program. So I felt like that would be a good thing to share. Let me share screen on the first of these three, which is the anatomy of Mina protocol. And if y'all want to open the links on your own computers, then you can also read it more precisely. And I'm going to zoom in. Questions before we start? Anybody have trouble accessing the links?
No, yeah, this looks great. I've been curious about Mina protocol.
Yeah, all
So I
right.
didn't.
So we can go ahead and get started with the first article then. So the first article is The Anatomy of Mina Protocol, How Mina Uses Snarks to Build a Constant-Sized Blockchain. This is feedback is encouraged. My content will include mistakes. This has not been like proofread by many people yet, so you should ask questions if things don't make sense to you. I'm going to basically paraphrase things that I'm saying that I've written, and then we can pause for questions whenever. So I recently became involved in Mina Protocol. It's an L1 blockchain. It uses ZK snarks to enable a whole new set of applications centered on user identity, privacy, and security. Currently, their blockchain uses proof of stake and a recursive snark mechanism to record new blocks, and they're in the process of launching ZK apps to their mainnet, which will bring smart contracts to Mina. While Mina shares a lot of similarities with other blockchains, especially Cardano, its consensus mechanism, called Ouroboros Samasica, also includes several snark-based innovations that are very interesting to dissect. A big selling point of Mina is that its blockchain is constant size, requiring only around 100 megabytes to host a full node, no matter how long the blockchain gets. Meanwhile, other blockchains like Ethereum require 1,000 gigabytes as of Q3 2022 to host a full node, and that number grows as the blockchain lengthens. So my goal here is to share what I've discovered about the MEV landscape on Mina, which is unique due to Mina's snark technology. However, there's a lot of prerequisite knowledge of Mina and its ZK apps required to understand the analysis. So I split this up in a 3-part series. In this post, we first explore how Mina protocol uses snarks and its consensus mechanism to achieve this constant size milestone in blockchain innovation. And if you look at their website, you can see that they emphasize this point a lot. Mina protocol, they talk about privacy, security, the world's lightest blockchain in terms of its size. And oh yeah, they, I guess, like to sell it as like 22 kilobytes of fixed size, although I think realistically right now what's in production is like 100 megabytes. But other blockchains increase in size as their blockchain lengthens. So you can also read through their website, and a lot of this information is drawn from me having conversations with these people, and it's a bit more condensed into this than what's available if you go scrolling through their websites and blog posts. But you could potentially piece together, I think, like 70% of what's in my blog posts based on like scrolling around the websites. Questions so far about Mina at a high level? Okay, great. Then let's continue. We start with a cursory overview of how consensus on Mina protocol currently works. For the full explanation, you can read the white paper. And in this case, the white paper is really complicated. So I think what I have in this is like a sufficient high-level overview. I think that the best starting point for reasoning about the current Mina protocol is to imagine a version of Bitcoin, meaning there's only payments, there's no smart contracts, a version of Bitcoin that is secured by proof of stake. So just imagine Bitcoin became proof of stake, but it still only supports payments, doesn't support any arbitrary execution of code. So from that starting point, we'll now add on some differences between how this and our mental image of proof of stake Bitcoin works. The big difference is that Mina represents this blockchain as a single recursive snark. And from our snark talks, we know what snarks are, and we know we know how to envision a snark. Each time a new block is added to the Mina blockchain, it is actually compiled into a snark. And that snark of the block, as well as the recursive snark for the previous head of the blockchain are combined and compiled into a new head of the blockchain, which is a new recursive snark that represents the state of the blockchain that has now added a new block. This is why the snark is called recursive. When we discussed like a snark, we talked about having a prover P and a verifier V, right? And then a circuit C. And the prover wants to show the verifier that they know arguments X and W, so that circuit C evaluated with X and W equals 0, right? In the case of a normal snark, this circuit has whatever arithmetic gates in it, multiplication gates, addition gates. We all remember a little bit what like this structure. That's what a normal snark uses in its circuit. A recursive snark, the circuit has one special property, and the recursive snark circuit, that special property is that that circuit, part of the arithmetic gates in that circuit is used to verify another snark. So you build up the verifier inside of the circuit that you're feeding into this snark. And so when this snark builds a proof, it is a proof that not only proves that like this circuit evaluates to 0, but in the process of this circuit evaluating to 0, verifies that a previous proof evaluated a previous circuit such that it became 0. That is what makes a snark recursive. And you can see that in this case, you're using the guarantees of like proof size, verification time, proving time, in order to represent something that would otherwise be a chain, like a chain of like blocks, instead as one proof that just keeps verifying itself across history. It means that what you have to currently store at any point in time on the blockchain is just a snark instead of the whole laundry list of blocks up until this point. Questions about this high-level overview? We'll get into the details of the specific implementation in a moment, but first, questions about the overview.
Yeah, so with the recursive snark, do you have to unwrap it fully in order to sort of verify it? Or how far back in the recursive process do you have to go each time?
So if you were to spin up a new node from scratch, you would either, number one, just trust that the current snark is valid because you don't have the tools if you're just looking at the snark to go and verify everything in its history. You can just trust that this snark is valid, and then you also have as input the current state of the blockchain, like all the global state variables of the blockchain, which is like the X, right? The X, the public input. That current state plus that snark represents everything you would need in order to start verifying transactions from this moment in time. If you were to want to go and verify all the transactions from the beginning of time, you would have to go through the process of like checking each one and then recursively snarking it and then making sure that it like still like works. But the benefit of that system is that you don't have to keep any of that stuff around, because all the snarking that had to occur in all those steps, like that part is all wrapped up in one recursive snark. This is contrary to I think like Bitcoin, where in Bitcoin you have to keep track of a list of all the unspent transaction outputs. And that requires like something that like basically grows with the length of the chain. But in this case, you don't necessarily need to keep track of all of that stuff because it has been rolled up into a recursive snark. And you just have to keep track of this current snark.
Yeah, all right, sweet. Thanks.
Let me unmute. So let's say I did want to verify from the beginning of time all the way up to the last block or the last, I guess I want to reproduce the current snark. Is that possible? Where would all that stuff get stored? It has to be stored somewhere, right?
Yeah, so in terms of the parts of the, I guess, transactions and block headers and all of those things, those are, I get the feeling that they're stored probably somewhere. I feel like I don't actually know. I think they would be stored off chain, but I think that I don't remember if that's something you necessarily need in order to go back and verify all the snarks are correct. I think that's a good question because if it is stored off chain, then although the chain itself, I guess maybe the correct way to phrase this argument about the constant size blockchain is that in order for you to get to the point where you can, I guess, go through the history of the chain and run it until its current state, you don't need to store something that's linear in the size of the blockchain once you get to the current state. But I don't know if you want like that level of detail in the transactions that have occurred in the past. I don't know if you need to like look at on off-chain sort of data that is stored about those transactions or those blocks.
Okay.
Yeah, that part is a little unclear.
Okay.
That's something worth looking into. I will look into that. Other questions? Okay. So here we're gonna dive into the specifics about how Mina's consensus protocol works. This feature of the recursive snark means that the nodes on the Mina network don't need to store a blockchain that grows with time. Instead, each node just stores a single recursive snark, which remains constant in size, making Mina incredibly lightweight to run. And so in order to better understand how Mina works, we'll break down some of the big questions for what this snark feature looks like. The first question is, what is being compiled into a snark? Each time a new block is being added, there are actually two types of snarks being created. First, each transaction selected for that block, which is like a payment, right? That transaction is compiled into a snark, which proves that this transaction was valid. It proves things that, you know, from Bitcoin, we like took for granted, like that the input summed up to equal the outputs, that the transaction has a valid signature, things like that. That is what one snark is built to prove. That snark only proves that this transaction's interior or the insides of this transaction are valid. But then the second thing that a snark is required for is to roll up all of these transactions into a block. Each of these transactions has itself been snarked such that it verifies that what the transaction tried to do is valid. And now there's a second snark that compiles the transactions into a block, and it checks that each transaction snark is valid. It checks that the block construction is valid, like the proposer is who's supposed to be proposing it, the block header follows the right format, things like that, and proves that this block is a valid continuation of the previous head of the blockchain, represented by the previous recursive snark. So this second type of snark is basically checking that the previous snark was done correctly, and now I have done some updates to my blockchain state using this new batch of transactions in this block, and now my new blockchain state is this, and my new blockchain state is valid. The second block is much bigger than the first snark because it's checking all these other things, but there's only one of these snarks, whereas this first type of snark, you need one snark per transaction you're trying to include in your block. And then this second snark is the one that's recursive because this third step requires within the circuit verifying that the previous snark was correct. And this second snark also rolls up the small snarks. Each transaction snark gets rolled up into it. And then finally, this snark is the one that is used to represent the new head of the blockchain. So the question of what is being compiled into a snark, there are two types of snarks being compiled. One takes the transactions, each of them, and compiles them into its own snark. And the second snark takes all those snarks, puts them together, and appends it to the blockchain. Questions about this first section?
So here, as far as the difference between referencing to snarks versus ZK snarks.
Good point. So far, everything I've said is that it uses a snark because it is not ZK. Mina protocol as it stands today is not ZK by any stretch of the imagination. And so I been very careful to not call these parts of the protocol ZK snarks.
Yeah, gotcha. And so it's just using snarks for the sort of optimization
That's right.
features, not for the zero knowledge features.
That's right.
Can I ask a question? So for point 3 here, when it proves that this block is a valid continuation of the blockchain represented by the previous recursive snark, what is it proving in particular?
Yeah, good question. So it has to check basically like so each of the transactions has checked some things. Like it checks that like whatever payment is being sent comes from somebody who has at least that much to send. It checks that it was a valid signature, stuff like that. This snark has to do things that's check, like for instance, that the ordering of transactions that this proposer chose doesn't cause some sort of revert or doesn't cause some sort of conflict on the chain. It needs to check that whatever this circuit claims is the new state of the blockchain is indeed true. That like if there was a previous state of the blockchain that had some storage slots and those storage slots had some values in them, and then these transactions for this block occurred, you're now coming up with a new set of storage slot values, right? And this snark has to show that all those new storage slot values were correctly computed from all the transactions that occurred. And so if one of those storage slot values is like the balance of your account, then it needs to show that this balance is now changed from maybe it was 0 before to 10 now, and it has to prove that that's correct. Those sorts of, I guess, high-level blockchain things that compose all the transactions together need to be checked here.
Okay, interesting. And that's different from 1, because 1 just checks that the transaction, like somehow the transaction, what's the difference between 3 and 1 is, I guess, my question.
Yeah, so 1 is checking things that are just, I guess, valid, necessary for each transaction individually. Like if there are n transactions in this block, then the n transactions will each have their snark. So there'll be n of these small snarks that do number 1. Sorry. Oh no, never mind. I've misunderstood your question. You're saying that you're asking like for this big snark, what is the difference between its role described in number 1 and its role described in number 3?
Right. I guess from reading it,
so,
it checks that the transaction snark is valid, but that doesn't show that the transaction is valid.
It checks that the transaction snark is valid, as in it acts as the verifier for that snark proof. But then the thing here is that snark proof isn't telling you what the new state of the blockchain should be after all the transactions have gone through. You need to produce a new state of the blockchain, new storage slot values for the chain after your block has been included, and then prove that that new storage slot set of values is the correct one, given all the transactions that just occurred.
I see. Gotcha. Okay, I'm clear on that.
Cool. So that's the first question. What exactly is being compiled into a snark? And by the way, the reason why I'm asking questions in this format is because I'm assuming that everybody has a clear picture of like how a proof of stake Bitcoin would work if it didn't have all these crazy snarks things. So if you do have questions about how a proof of stake Bitcoin would work, like you're having a hard time wrapping your mind around that, definitely ask those questions first, because we're starting from that premise. So in addition to first asking what is being compiled into a snark, the second question here is who's responsible for building each of these snarks? Because remember, there's always a prover and a verifier in a snark system. Who is the prover in all of these cases? We sort of know who the verifiers are because we are outlining who is in charge of verifying things, but who exactly is in charge of proving things? Each time a block proposer, so proposers in a proof of stake system, each time a block proposer decides on the transactions to be included in the next block, they are responsible for building this second snark, this big snark. They're responsible for building the big snark. The one that's recursive, the one that represents the updated state of the blockchain. However, what the block proposer does not do is the block proposer does not build the snark for each of the transactions. It doesn't build all of the small snarks. They instead outsource the construction of the small snarks, validating each transaction individually to a group of users called snark workers. These snark workers are not block producers. They're completely separate. The snark workers compete inside of a snark marketplace for the chance to compile each individual transaction into its own snark. So you can think about it as like, we need both of these snarks to be produced. The person proposing the block produces a second type of snark, but the person proposing the block, sort of like separation of responsibilities, doesn't produce the first type of snark. Instead, there is a whole marketplace of these snark workers who will get paid for the outsourced labor of compiling each of these small transactions into its own snark. There are a couple of reasons why this is the case, and we'll get to why this setup was chosen in a little bit. But questions so far about like what exactly this what exactly this means. So given that we now understand that there is block proposers, just like in a normal proof of stake system, that will compile the big snarks, and we have snark workers that compile the many little snarks, we can ask ourselves, how does this all flow together into a timeline? If you already tell me the timeline of how a block is proposed, what step occurs when? When does each snark get built? If you and I were talking about this without any knowledge of Mina, this is at least what like my first intuition for what a timeline of events should approximately look like. So this is our like naive first try at building Mina. Let's say, okay, the proof of stake protocol randomly selects who the next block proposer is going to be, right? Use some verifiably random functions, just like any old proof of stake consensus protocol. That block producer who has been chosen randomly selects some transactions from its mempool, maybe just the ones paying the highest fees, and decides they'll include those in the next block. That block proposer then pays snark workers on the snark marketplace to compile each of the transactions they chose into a snark. So they have n transactions that they chose. They'll pay n snark workers, and those n snark workers will produce n snarks, one for each of these transactions. The snark workers produce the transaction snarks, and then the block proposer combines the snarks and the block into a recursive snark representing the new state of the blockchain. Ta-da! Very straightforward. There are issues with this timeline. So this naive first attempt at a timeline isn't going to be the one that we stick with for a few reasons. Well, one big one. This timeline can introduce some issues, namely that a block proposer may be incentivized to choose transactions that are cheaper to snark for their block, thus effectively censoring more complex transactions that would require more expensive snarks, because the block proposer has to pay the snark workers in order to compile their transactions. And so they want to pay as little as they need to in this step. They want to maximize the fees in this step, but they want to minimize how much they have to pay in this step. And you assume snark workers are going to like charge more if a certain transaction, the circuit involved in the snark is bigger, has more multiplication and addition gates or something like that. And so there'd be like this sort of conflict of interest if the block proposer were also the one trying to compile the transactions in the snarks. That's also why you outsource the labor, because if the block proposer have to deal with this second step, it'll also cause this sort of bad incentive where you only want to include transactions that are simple to snark. So how does Mina fix, or at least mitigate, this problem? To help mitigate this misalignment of incentives, the true timeline of events on the Mina blockchain is closer to the following. We start with the same thing as before. The proof of stake protocol randomly selects the next block proposer. The block proposer chooses some transactions from its mempool to include in the next block. It maybe chooses the ones that pay the highest fees, sure. Now this is where the differences emerge. That set of transactions that it wants to include in the next block, they don't get snarked right away. Instead, they get added to a temporary blockchain that is basically, imagine just a linked list only consisting of transactions and blocks that haven't been compiled into snarks yet. It is a temporary blockchain that is just storing the unsnarked transactions. This temporary blockchain is short, but it is not empty. And what I mean by that is there will always be a queue of transactions that end up on this temporary blockchain that haven't gotten a chance to get snarked yet. There is a delay between when a block proposer chooses the transactions and when the transactions get compiled into snarks. And this delay is intentional. What is causing the delay? The delay is that when the block proposer has chosen the transactions and the transactions get added to this temporary blockchain, the block proposer then pays snark workers on the snark marketplace to compile the transactions from the oldest block on this temporary blockchain into snarks. So the block producer is still paying the snark workers, but the block producers is paying the snark workers to snark transactions that are not the ones it chose. It is instead paying the snark workers to snark the oldest transactions that haven't been snarked yet. So it has to pay for transactions it didn't choose. And as a result, there's not this misalignment of incentives to only choose transactions that are cheap. Because you're not going to be the one to pay for your transactions to get snarked. You can choose expensive ones. You don't have to worry about how expensive or how cheap it is, because you're not likely to be the one paying to snark them later on. In this way, you're introducing a delay, because the next proposer down the line has to be the one to pay for your snarks. So it takes slightly longer for each block of transactions to become fully converted into a snark and for them to be fully appended to the blockchain. The rest of the process is similar in that the snark workers that get paid produce the snarks for those transactions. And then this oldest block is removed from the temporary blockchain because its transactions have been snarked. And then the proposer, when this proposer's block becomes the oldest one on the temporary blockchain, and then some future proposer has paid for the snark workers to turn these transactions into snarks, then that proposer's block's transactions will be compiled into snarks, and then that block producer will then create the big snark from all the small snarks. So at that point, the transactions that started out in step 2 will finally be put onto the blockchain. This timeline means that the block producer is incentivized to include transactions, whether cheap or expensive to snark, in their block. The price for snark workers to build those transactions will be paid by a future block producer and not them. And this is a nice diagram of this timeline from the white paper, which summarizes basically the things that I described. There is a verifier executes a transaction, enters a mempool, it is gossiped through the network. This is just like similar to proof of stake in general. Meanwhile, some snark workers make snark proofs for unsnarked transactions. This is like the snark marketplace. Next, the block producer is selected to produce a block. The block producer looks at their mempool, selects the most profitable transactions to add to the block. The block producer must also add snarks to the block in equal quantity to the transactions that they've added. So it's saying that they have to go and pay for the snark work on the oldest transactions, not their own, but for the oldest transactions in this temporary blockchain, and while their transactions get appended to the temporary blockchain, but don't get snarked yet. The snarks that the block producer must add have to correspond to unsnarked transactions that are part of this queue, or this temporary blockchain. Each recently added transaction has its own ordered book of snarks, all competing to offer the best price on this snark marketplace. And so the block producer looks at the snark order book for each transaction and purchases the cheapest snark that a worker is willing to produce for it. And then once the block producer has paid the snark workers for the snarks for their transactions, then the block producer will add their new transactions and their new snarks to this queue. And the block producer will then compile this block into like the next, I guess, head of the blockchain. And so this queue will now have these sets of snarked transactions officially appended to the blockchain, and this will be the temporary part. This is now the new temporary blockchain because this is the part that hasn't been snarked. The queue state is updated to maintain a constant size. The reason it is constant size is because every time you add a new transaction, you must snark an existing one. So the length of this queue isn't supposed to lengthen over time, isn't supposed to grow over time. And the block producer updates the ZK snark for the blockchain with these now snarked transactions. And then the new block is gossiped and validated. Questions about this whole timeline?
Can we go over this whole incentive thing? So the block proposer's incentive is to include those transactions which give the highest fee. Snark workers, they're motivated to choose the cheapest. Is it because they get a fixed fee for each snark, and so they're motivated to choose? That's not true, right? Why are they motivated to choose the cheapest ones?
The snark workers don't get a so when you're a snark worker, you're faced with a pool of unsnarked transactions. And those unsnarked transactions may cost varying amounts in order to be snarked. You, as a snark worker, get to propose prices for how much you want to get paid to produce a snark for each of these transactions. Likely, you will ask for more money if the snark is going to be more expensive for you to build. And then because you're part of the snark marketplace, there's like an order book of like all the prices that snark workers offer in order to build a snark. And the block producer will, among all the, like, I guess the bids by different snark workers for the same transaction, they'll choose the one that's the cheapest. And that snark worker will get a chance to build the snark for that transaction. But the only things that you as a snark worker are allowed to try to snark are the ones that haven't been snarked and are the ones that are the oldest. Because if you like waste your time bidding for a transaction that's not the oldest, the block producer is not going to buy it because the block producer isn't trying to, pay for that transaction to get snarked yet. So as a snark worker, you don't have the choice of, you don't get to choose which transactions to snark or not. The transactions you snark are the ones chosen by the block producer or like a previous block producer that enter this temporary blockchain.
I see. So those transactions chosen by the previous block producer are the oldest transactions in the temporary blockchain now. That's
Yeah.
the significance of oldest.
That's right. Yeah.
I see.
I'm wondering,
And-
do you have a gauge on how expensive we should expect snark workers to charge?
That's a good question. I actually don't have a good sense of order of magnitude just because I haven't personally run a node on the Mina network. I do know that it is a system where because the network will not be, because the blockchain cannot lengthen until something has been snarked, the price that a snark worker can charge for a snark will grow over time as it like takes longer and longer for a snark worker to become willing to snark it. So if you are a block producer, you are going to get slashed if you are unable to produce a new block, right? So it is in your incentive to pay more and more as like time goes on so that you don't get slashed. And as a result, if snark workers are scarce, snark work is going to become more expensive. If there's only one snark worker in the entire universe, then that snark worker can charge whatever price, and the block producer would have to pay it because they need somebody to snark their transaction. In that case, that there's only one snark worker in the entire universe, the block proposer might as well go and become a snark worker too, and do both sides of the job.
I mean, being a snark worker is pretty easy, right? You just like run some open source software which does the snark working for you.
Yeah, I imagine that is similar to running a node. Yeah, it's something that can be pretty heavily automated.
I guess like the main potential complicated thing is if you come up with proprietary optimizations to your snark worker.
Yeah, I'm sure that there are ASICs out there, like custom built GPU or whatever units that are better for verifying snarks and stuff or producing snarks and stuff.
Cool. And another question I had is how long this delay is. How long is the temporary blockchain?
Yeah, so that's a good question. I think in practice, let me actually double check my notes.
Yeah, I actually at ETHSF, one of my friends built on Mina protocol, and he told me the block time was like 3 minutes or something like that. I'm not sure how that...
The block time is, I would say, yeah, it's escaping me now because there's two senses of block time. There's a sense of like block time as in how long does it take for your block to reach the temporary blockchain, and then there's a sense of block time as in how long does it take for your block to become snarked and enter the real blockchain. And I think that the former is closer to like within a minute or something. But the latter, I guess, could be 3 minutes, could take longer. Yeah.
I'm wondering what's like the failure mode for a transaction included on the temporary blockchain not making it to the actual blockchain.
So the failure mode here, the good news is once that has been included onto this temporary blockchain, the consensus protocol mandates that it must be snarked. right? There's no way for someone to drop it from the
Mhm.
temporary blockchain, just because like there's
Yeah.
blockchain finality, just like in proof of stake, right? Like
Yeah.
proof of stake has block finality. After this block's been proposed, it's not going to change. The only way that transaction can be dropped is if the whole block gets dropped in a block reorg.
Okay.
And if there's a block reorganization, then that might occur. And we're going to talk about that once we get to the MEV part
Okay. Sounds good.
of the series.
So it really is sort of when it's on the temporary blockchain, it's sort of on the blockchain basically, unless there's a reorg, but that's like possible on any blockchain.
Right. So in that sense, it's like as good as confirmed, but it's just not in the snark form. It's not in its final like compressed format yet.
Yeah.
And it's called a temporary blockchain, but why is it called a temporary blockchain and not just a bunch of transactions?
So I just call that temporary blockchain just for ease of imagination in my mind. Like this timeline calls it a queue. It just calls it the queue. I guess it's all the same in this case because there's not that much fancy stuff going on in terms of like I don't know, consensus and things like that. It kind of sort of is a queue. Yeah.
But I mean, one reason to call it a blockchain is there is consensus going on it, right? Like you do need to reach consensus on which transactions need to be snarked.
Yeah, so in that sense, it is something that like you need consensus of the chain in order to have any like meaning to it. I guess the other characteristics of a blockchain, like block headers, coin bases, things like that, I don't think those, I don't know. I don't think that those are a part of this like queue. So it is missing some of the other aspects of a blockchain. But fundamentally, yeah, it is something that has to be gossiped around the chain. It has to be propagated through the P2P network.
Gotcha. Okay.
So yeah, this Snark-based blockchain is very unique, and it allows Mina protocol to be hosted on much more lightweight devices, possibly even inside web browsers than other blockchains. As in, you could run a Mina like light client inside your web browser because all it needs to do is verify snarks. It doesn't need to store nearly as much stuff as another blockchain would do, and verifying snarks is relatively cheaper and requires fewer resources. So that's like the main selling point of current Mina. This concludes the first of our three-part series on Mina protocol, as new ZK apps update and MEV on Mina. So now we'll move on to the next segment, which is going to be about smart contracts on Mina. Because remember, everything that's happened so far is only for payments. It's only supporting payments up until this point. All right, let's move on to part two. Smart contracts coming to Mina. ZK apps will enable privacy-centered applications on Mina protocol. In its current state, Mina protocol is already powerful, using ZK Snark technology to represent an entire blockchain in one single snark. However, its functionality still resembles that of Bitcoin, primarily useful for payments, but limited in other respects. The ZK apps update will bring smart contracts to Mina and boost its functionality to become equivalent to Ethereum rather than Bitcoin. In addition, these ZK apps will use ZK snarks. Notice that I'm using the word ZK now. It is a ZK snark to shield user data and make smart contract transactions somewhat private, something that Ethereum cannot do. The ZK apps update is currently live on the Berkeley testnet, which is like the Mina testnet, and is set for launch on the mainnet by 2023. And in this post, we'll dissect how ZK apps will fit into Mina. All right, questions about this high-level introduction?
This is sort of going back a little bit, but I'm wondering what accounts for the difference between the 22 kilobytes and the 100 megabytes.
I think that might just be that in this current state, they haven't maybe they haven't optimized some things about maybe they haven't optimized some things about the snarks that they're using. Maybe it's that like if they wanted to, they could make the snark sizes smaller, but that might possibly trade off with proof construction time and verification time. So like maybe this size blockchain is vastly faster to produce proofs for and verify. And so when they want to make a selling point out of the size of it, maybe they talk about like that more extreme version of the blockchain.
Okay, cool. Yeah, makes sense.
So let's dive into the overview of what ZK apps are going to bring to Mina. We can start by reasoning about ZK apps through reviewing Ethereum smart contracts. This is a simple overview of how a smart contract on Ethereum sort of works. First, a smart contract starts out maybe as a program written in Solidity. Oh no, typo. Which is then compiled into EVM bytecode. Then each of these smart contracts is deployed to an address where its EVM bytecode lives on-chain. Each smart contract has some persistent memory called storage available to it on-chain, which transactions can modify if they wish. And then a user can interact with the smart contract by creating a transaction, specifying the address of the smart contract, the function of the smart contract they want to call, and the input data they want to pass to that smart contract function. The user will then propagate this transaction across the mempools of nodes in the peer-to-peer network for inclusion into the blockchain. And each node will execute the smart contract transaction and using the input data to check that this transaction is a valid one, and also check that the signature is valid, things like that. And each node will, if it recognizes the transaction doesn't execute successfully, like it reverts or it runs out of gas, each node will throw it out. And if it executes properly, then each node will consider including the transaction into its next block based on the amount of fees that it's paying and things like that. This is like a high-level overview of like how Ethereum smart contracts works. We're starting with this because now we're going to talk about how ZK apps work, starting from this timeline and then making modifications. So the basic premise of ZK apps follows the logic up here, but differences exist which allow ZK apps to preserve user privacy and integrate into Mina's Snark-based blockchain. So we're going to go one by one through these. On Mina, a ZK app is written in the Snarky.js language, which is sort of a version of JavaScript that has some custom features to it that interplay with snarks. So Snarky.js is the language as opposed to Solidity for like Ethereum. The ZK app is then compiled into a ZK Snark circuit C with corresponding prover P and verifier V. You can sort of think about it like instead of compiling into EVM bytecode, you compile it into circuit with like prover and verifier things. The circuit has public information X and private witness W as inputs, such that the prover wants to show the verifier they know a witness such that the circuit evaluated for X and W equals 0 through a snark proof. I may sometimes just say snark for brevity instead of the word snark proof through the rest of the article. And the asterisk here says, this is technically the framework for the Groth 16 snark, which we are all very familiar with because of the previous talks. But the Groth 16 snark framework is actually technically a simpler system than what Mina uses in production. However, it is sufficient to think about it in this like paradigm of like circuits and X and W and stuff for just the purposes of abstractly reasoning about ZK apps. So I'm going to reference this setup a lot, but just know that like in production, what Mina is actually using is a snark setup called Kimchi, which is an offshoot of Plonky 2, which is a successor to Plonk. So it is a different proving system than Groth. So we've talked about how on Mina, it's the Snarky.js language, and it is compiled into circuits with provers and verifiers, as opposed to Ethereum, which uses Solidity and is compiled into bytecode. The second step here, the source code of a ZK app does not live on chain. Instead, the only thing that gets put on chain is the verifier V. That is deployed to an address. And you think about this because like the point of the blockchain now is not to execute the code. The point of the blockchain is just to check that the snark of the code is probably correct. And so they don't need to send the source code to the blockchain. They just need to send the verifier to the blockchain. And that source code, as a result, does not have to go on chain. The source code is instead distributed off chain to the desired users of the ZK app, which can be everybody. It can just be posted onto the internet, or it can be exclusive. It can be source code sent only to a few people. Then the third step. Each ZK app does have some persistent on-chain state, but it is very, very limited. Each ZK app can only have a very small amount of persistent memory, I think around 8 bytes of persistent memory on-chain. I think this is part of the effort to keep Mina lightweight. You don't want the state space of the chain to explode. And In particular, the on-chain state of a ZK app must be part of the public information X of any ZK snark, because this on-chain persistent memory is being shared with all the nodes in the peer-to-peer network, and it's being shared in its raw form. It is not being shared in a shielded, like snarked form. So the on-chain state of any ZK app, you can think of on-chain state as things like user balances or whatever. Those things are not zero knowledge. Those things are not private. Those things are public, just like they would be on Ethereum. And each node stores a copy of the state. So then, number 4, step 4, how a user interacts with this ZK app. This is where the big differences start to emerge. So before we get to number 4, any questions about like these parts 1 through 3? Okay, so let's talk about number 4. A user can interact with a ZK app by assuming the role of the prover P. So notice that the ZK app on chain is the verifier V, and now we as a user, we're going to assume the role of the prover P. So what do we as the prover need to do? First, let's figure out what is the address that we want to call on chain, figure out what is the function of this ZK app that we're aiming to call, and figure out what is the input data we want to send to this function. Those are pretty much similar to what you would do for Ethereum. In this case, the input data we'll also split up into 2 categories. The data that we think can stay public, which will be X, which is the public data part, and some of the data that we want to keep private, which is the witness. These are the things that we'll figure out first, off-chain, just privately. We'll figure out this stuff as the user. The second thing is, we'll also have to make sure the ZK app's previous on-chain state and the new updated on-chain state after this transaction is executed are also part of the public information X. Just because like this is a corollary of part 3. Like we need to make sure that the on-chain state is public and it's part of X, because otherwise like each node has to store a copy of it. There's no way it can be private. After we have taken account of all the the pieces of data that are going to be involved in this ZK app transaction, what we'll do is compile a ZK snark based on this circuit that we have, based on the source code that we've been handed off-chain. We can compile a ZK snark proof showing that our function call to this ZK app at the given address with this input data X and W results in a valid updated on-chain state, and that new on-chain state is also provided in our public information. So as the user, we are executing the smart contract off-chain on our own, and the only thing we send to the chain is the proof that we did it correctly. And note that the important thing here is because we have to do this smart contract execution off-chain, we need the source code in order to produce this snark proof. If we do not have the source code for the ZK app, the user can't create a valid ZK snark, because without the source code, you don't know what the circuit looks like. And if you don't know what the circuit looks like, you cannot create a valid proof for it. So if you're a ZK app and you don't want anybody in public to use your application, you can try to hide it from them. And if they don't have your source code, they can't interact with you. And so you might want to just share your source code with people you trust and people you want to interact with your ZK app. Obviously, if they share it with somebody else, you can't control that, but that is one, I guess, feature of Mina. And so this overall is the way a user interacts with a ZK app. And so what ends up being sent by the user to the chain is this proof. It is the proof that, hey, I've interacted with this ZK app and I have produced this new on-chain state, which is maybe that my user balance has increased. And I'm submitting this proof that shows that everything I did was valid. And the only thing the chain will do is the chain, being the verifier, will then check that the ZK app transaction snark is valid. So here, the chain doesn't re-execute the code. Every node on the network is not executing the code as it would be in Ethereum. Instead, each node is just verifying that the transaction that the user did off-chain is correct. And if the verifier rejects this ZK snark, then the node throws out this transaction. But otherwise, the node will include this transaction, meaning that it'll update its on-chain state for this ZK app to be the one after the user has interacted with it, and it'll eventually get rolled up into the bigger blockchain. Questions about how this ZK app workflow works?
This is cool. One thing I'm thinking about is the ordering of transactions and whether the proofs become invalid under some conditions, or if that's not too much of an issue.
No. You're bringing up an incredibly valid point, which is this produces some. I mean, obviously, like if two people try to send a transaction at the same time, then they're both using the same starting state of the blockchain in their snark, but they're both, using different ending states of the blockchain in their snark, and so you kind of have to pick one of the two. You can't have both snarks be valid. That is actually the same issue can occur on Ethereum. Like if two users send conflicting transactions, only one of them can include it. So while that is like an issue, it's like something that all blockchains face. If those two users are creating snarks that result in different parts of the on-chain state being modified, I think there is a solution being engineered such that you can compose their snarks together, even though like one snark after the other may not be feeding in exactly the same state. I think that is something that the snark technology is being built to handle.
Yeah, cool. Makes sense that it will be possible.
Yeah, but that's definitely one of the
sounds like
the
some
first things that
complicated stuff.
yeah, it's definitely one of the things that that the team has like spent a lot of time engineering around, because it's not trivial to think of a way to like get it so that when two snarks are both sent in, that they're able to be composed, sequence one after the other.
What does it mean? What's an example of two transactions being sent given the same input data? And so you're saying the same two transactions are sent given the same input data, they produce different outputs?
So it's like there's a on-chain order book and someone has placed like a bid, and two transactions both try to hit the bid at the same time. Only one of them is going to be valid. But I think what Cole's mentioning is even something simpler than that. It's like, say there's a smart contract bank on chain, and I send in a transaction that is supposed to be a deposit, and then you also send in a transaction that's supposed to be a deposit. When we are building the snarks off chain, the starting state that we build it with might have everybody's deposits at 0, and then each of our ending states might be that our deposit is now non-zero. But when you try to append the two of them together, you can't append it in a straightforward way, because then it's going to think that the snarks, the second snark is wrong, because the second snark's starting state is not the first snark's ending state. And this is something Ethereum doesn't have to deal with, because in Ethereum, you just have to execute the code. And as long as the code executes, it doesn't matter what the starting state of one transaction was and what the ending state of the other transaction was.
I see.
Cool. So now we ask a few clarifying questions about like understanding how this like ZK app workflow guarantees some sorts of privacy. What part of this ZK app is private? Mina ZK apps offer some, but not complete privacy. So let's split it up into different parts of the data. The data that is treated as persistent memory, or like the on-chain state, that part's not private. As I've emphasized several times now, that part is public, because each node will record this on-chain state in its raw form, not in a shielded ZK app, a ZK snark form. It'll just record it as those numbers, like your balance is 10, your balance is 20. That part is not private. However, these other parts are. The input data that any user is sending in, that part is private, because the user does not ever do the execution of the code on chain. The user input data always stays off chain, and when the user places that input data into the witness, the resulting ZK snark will not reveal any information about the input data either. The only thing that is slightly problematic is if the resulting changes to the on-chain state are public, it may betray the nature of the input data, because like if like I have a ZK snark that like basically like increases the balance of my account on chain by 10, you might assume that one of my input data is probably the number 10, which is like the amount I want to deposit, right? You can make those assumptions, and those are probably true. So in some ways, like you can make some judgments about like what the input data could have been, because there is persistent memory on chain that betrays a little bit of it. But in general, things like for instance, if you are onboarding to this bank and you need to prove to the bank, like do some KYC procedures with this bank, if you were to do this on a blockchain like Ethereum, you would have to submit like that sort of documentation, like your passport or your driver's license, and that thing would become public on the blockchain, because the only thing Ethereum can do is be public. But in the case of Mina, if you're interacting with the ZK app, if your passport or your driver's license is part of the input data, that input data never goes on chain. What arrives on chain is just a proof that your input data, when it was sent into this application, was processed successfully, resulted in a valid snark that says you have passed KYC. And that part gets sent to the blockchain. But your passport and those pieces of information do not get sent over. And so that is why the input data being private is useful. And the third part that's a piece of data to us is the source code. The source code of any Mina ZK app is technically private because it is not stored on chain, but users of a ZK app must have that source code, and they can share it with anyone. So the source code can gradually become public. So while the privacy of ZK apps is not as all-encompassing as, say, Zcash, and you remember we talked about Zcash, which is a completely anonymous blockchain version of Bitcoin, right? Like in Zcash, you don't know who sent what money to who, when. You don't know any of those things. This degree of privacy is not available on Mina with ZK apps, but what Mina does offer in terms of privacy is already very powerful. The example of like the passports I just said, and also, for example, something that, like, I guess just reading this example out, if there's a ZK app that issues loans to users with high enough credit score, each user does not have to make their credit score public to the blockchain in order to take out a loan. Instead, only a ZK snark proving the user's credit score is high enough for this loan will be propagated to the blockchain, while the user's raw credit score remains hidden as the witness W portion of the input data. So questions about this analysis, like what makes ZK apps private?
Well, I have a question about what the like public on-chain state looks like. Like, is that just like a Merkle tree with a root? And like, is on-chain state basically like a Merkle tree of all the account balances?
I imagine it's probably stored like that, yeah. Because I think is Ethereum stored like that? I don't remember. I would guess, yeah, that's probably how they store it. And then like the actual values are probably held off chain by the individual users or applications that care about it.
So what does it mean for that to be public? Like, why? Maybe I should think about how to phrase my question better, but like when I determine like what part of like the information in my transaction to be public or not, like why is it that like the on-chain state needs to be public?
So I think that there is a version of Mina where this is not the case. I think there is a version of Mina that can be built where this part just exists as Merkle proofs, or like, sorry, Merkle trees, and it could all be private. I think the answer to this question is actually just because current Mina protocol was built without ZK in mind. So in current Mina protocol, your on-chain state is public. Well, your on-chain state is just like your user balances of like Mina token, because it's just supporting payments. But that on-chain state is already just public and it's not shielded at all. And this ZK app is sort of being built on top of that existing infrastructure. And so it is borrowing that infrastructure in the sense that the memory that it's using and the on-chain state that it's working with is structured the same way as Mina protocol is right now. So I think that is the main reason why it is not like shielded in some Merkle way. So I guess the short answer is path dependence. I think that what you're mentioning about like it being stored as Merkle proofs, or like as a Merkle tree, I think that is a valid thing to explore. Yeah, I'll ask that question to Brandon. which, by the way, Amy has read through this set of articles and also already brought up another point, which I guess we'll get to maybe later when we get to the MEV portion, that I also went and asked Brandon about. So these sorts of questions that y'all have about this content are going to make it to the ears of the Mina people. And I know that we're running out of time, so we're going to cover part 3 next time, but I'll just very quickly wrap up this segment of the series. So what is the vision for ZK apps? Currently, ZK app functionality is available to developers on the Berkeley testnet. You can use this guide to get started. There are endless use cases for ZK apps, most of which have not been thought of yet, but I'll share one very cool use case here, which is the KYC example that I just talked about. So we don't have to read this one. The moral of the story with the KYC example is that this use case leverages the composability of different blockchains. Basically I'm saying that like if you're a decentralized exchange on some other blockchain like Ethereum, you might just offboard your KYC workflow to Mina, as in you bridge to Mina, do the KYC stuff privately, and then bridge back to Ethereum after you're done. And that way, Mina gets to handle the part of your onboarding process that's privacy sensitive, and then the rest of it, you trust Mina, and then you continue on your way in public Ethereum space. So this use case would leverage the composability of different blockchains so that Mina protocol is used where it shines brightest, specifically handling privacy sensitive logic for any application. In fact, the NIL Foundation has already built a bridge for current Mina to Ethereum, so it'll only be a matter of time before a bridge for ZK app to Mina to Ethereum is built. This is sort of the big vision of like how Mina can be used as a niche, like privacy guaranteed application for other blockchains to use. Although Mina, of course, would love to have its own ecosystem and have like stuff built on its blockchain and that stays on its blockchain. So with this introduction to ZK apps on Mina, we finally have all the context required to analyze the forms of MEV present on Mina compared to other blockchains, which I guess we'll cover next time.